Welcome back to ch205. In this video, I'll be talking about stiff ordinary differential equations, section 5.4 on page 108 of the textbook. So let's understand first what stiff method or stiff ODE is. If you have a problem with two requirements on delta t that are vastly different, then the problem called stiff. Okay, for example, I have a differential equation like this. Okay, y prime is minus a is a constant times y plus a function of time st. Okay, with some initial condition. And I want to solve this. So if you want to really solve this analytically, then you integrate both sides, right? And if you look at only this piece is our toy problem we had before. This is the solution to this piece is an exponential function, which is right here. And then the solution to the rest of it is something like this. So the goal is actually not really to find the exact solution, to use the exact solution and understand what stiff ODE is. So if you accept that the solution would look something like this, then if a is very small, okay, so if a is very small, then this function actually decays very slowly, right? In contrast, if a is very large, then this function is going to decay very fast. So let's stick to the regime that a is large. Then this function is going to decay very fast, and if something decays very fast, and we want to solve for the solution with good resolution, then our delta t should be small too, right? So basically our delta t should be something like proportional to 1 over a. Okay, if a is very large, then 1 over a is very small, and then delta t should be small. Okay, so in case that a is large, then we prove that delta t should be small. If a function decays very fast like this, then our increment along the time axis should be small to be able to resolve this really nice curve that goes down or decays. Alright, so for this piece we need a small delta t. How about here? Well, if our maximum time that we're integrating is large, let's say this t, well, this t is different from the delta t that I use here. This t, if this t is large, which means I have to integrate this function over a large period of time, then with the small delta t that I chose to resolve the resolution for this function, okay, make me solve this, or maybe make me create a spreadsheet with many lines, because if delta t is small and t is large, then I have many delta t's in my 0 to t interval, right? So from 0 to t interval, we're going to have many of the delta t's because delta t is small and t is large, and so that requires a lot of spreadsheet lines or a lot of calculations. And so if, let's say, if this is 10 to the 7, let's say t maximum t is 10 to the 7, and my delta t is 0.1, okay? So that means you need to have something like 10 to the 8 rows. That's about 100 million rows, right? So Excel cannot afford this. It doesn't provide that many rows. So this is called stiff problem, right? We have two different time scales. One is, let's say, for this function, the other one is the maximum time here, and the delta t that we use cannot resolve this maximum time because there are many rows required. Okay, so let's look at one problem here. Let's have a differential equation like this. Could be a reaction equation, right? You can think of y as concentration of one reaction, z concentration of the other, or y is the concentration of one species, and z is the concentration of the other species. Okay. If you solve this using forward Euler, then we get something like this, right? So yn plus 1 minus yn for the left side. For the right side, we get dt times the right side at time n. That's what I have here. And for the bottom equation, we have zn plus 1 minus zn is equal to dt times the right side at time n. So, no problem. Let's hard code this into the spreadsheet. So I'm going to move this over here. Here's my spreadsheet. I'm going to move it over here. And here's the forward Euler. Let's say the initial condition is 1 on 0, and my delta t is 0.01. And I'm going to look at the problem only from 0 to 0.1. Well, this is actually a small range, but we're going to see how forward Euler behaves even within this small range. Okay, so this initial condition, what is yn plus 1? Well, it is yn, the blue cell, plus delta te times the right side of this, which is minus yn plus zn plus 3. Okay, fine. And what is zn plus 1? Well, zn plus 1 is going to be, according to this, is going to be the current z plus delta t, and then times minus 1 times e to the 7 times z, or zn plus yn. So zn yn. Okay, fine. Enter. Let's copy these or highlight these, drag down, and you see that the solution goes, actually blows up. So from initial condition 1, 0, it goes to 10 to the 36 and 10 to the 43. These are huge number, right? So most likely the forward Euler doesn't work. I mean, the solution can go so fast from 1 to 10 to the 36. It's unreasonably large. Okay, now let's do backward Euler. So if we're going to do backward Euler, the discretization goes like this. Yn plus 1 minus yn left side. Right side should be at n plus 1. So it's dt, everything at n plus 1, right? Minus y plus 1 minus plus zn plus 1 plus 3. Second equation, zn plus 1 minus zn is equal to dt times the right side at n plus 1 is minus 1 e7 times zn plus 1, right, for this term, and then yn plus 1. Well, we have two equations, two unknowns. Yn plus 1 here, here, and zn plus 1 here, here, here. So these are coupled linear system, right? And the unknowns are zn plus 1, yn plus 1. So you can solve two equations, two unknown from before, from your calculus, your linear algebra. You know how to do this, right? So what we're going to do is we bring all the unknowns to one side and all the knowns to the other side, and that's what we get. Okay, so 1 plus dt yn plus 1 minus dt zn plus 1 is equal to yn 3 dt. So actually I moved these two to the left side and this guy to the right side because that's known. I do the same thing for the second equation. I get these two. So these two are basically these are obtained by rewriting these two equations. Okay. Next, we look at these two, and if I multiply the first one by 1 plus delta t, I multiply the first one by 1 plus delta t, and multiply the second by, I'm sorry, if I multiply the first one by dt, and multiply the second one by 1 plus dt, then yn plus 1 goes away. Okay, so if I multiply again this by dt, the second one by 1 plus dt, and then add them up, okay, so then yn plus 1 goes away, and then I can directly solve for zn plus 1. So this is the equation we get. We can directly solve for zn plus 1, and zn plus 1 is going to be this right side divided by the left is all dt's and some numbers. There's no yn plus 1 anymore. So from this equation we solve for zn plus 1. Now we know zn plus 1. We plug into the first equation here and then solve for yn plus 1. Okay, which is going to be this plus this divided by this. And that's what I have here. Okay, so I have two equations for zn plus 1 and yn plus 1. I can go ahead and hard code these in a spreadsheet. So here is spreadsheet version of it. Okay, so first we're going to solve for zn plus 1. It's a little bit long, but I think nothing special. It's going to be from here. It's going to be dt yn. So here's dt yn plus 3 dt plus 3 dt, and then plus 1 plus dt times zn. So plus 1 plus dt times zn. And this whole thing divided by denominator, which is going to be 1 plus dt. So here's 1 plus dt, and then 1 plus dt e7, dt 1 e7. And then minus dt squared. I think I forgot this piece, which I need to implement that. So I missed that one. Okay, minus dt squared, and we have to freeze the indices because dt is not changing. Okay, so that is my Zn. So this is Zn plus 1. What is Yn plus 1? Well, that is going to be Yn. So here is Yn purple cell. I'm sorry, the blue cells is Yn blue cell plus 3 times dt, and then plus dt times Zn plus 1, so the purple cell, and then divide by 1 plus dt. I think that is a Yn plus 1. So we're going to hit enter. I'm going to highlight these two and then drag down. See? The solution actually is within the range. The concentration is actually increasing very, very slowly. And this guy is also increasing very, very slowly. So compare the two solutions here and here. So you see that actually error goes up really, really fast in forward Euler. In backward Euler, the error is very, very small. Although both are first order, but backward Euler actually behaves much, much better. The reason is for stiff method, okay, for stiff method we have to use what is called implicit methods. Implicit methods are methods that both sides of the differential equation after we discretize becomes function of n plus 1. Like in this case, remember for backward Euler we had n plus 1 on this side and also on that side. So we have one n plus 1 here, and then n plus 1 variables on the right side as well. But for forward Euler we have n plus 1 variable only on one side. So this is called explicit method. The forward Euler is explicit method. This is called implicit method. And so backward Euler is implicit method. For stiff methods, or for stiff problems, okay, for stiff problems where we have two or more than two different timescales that requires small delta t and maybe a large t, then implicit methods work the best. And one of the implicit methods is backward Euler. Again, implicit method is a method in which both sides of the differential equation, when we convert them to n and n plus 1, both sides become function of n plus 1, right? Like in this case, we have n plus 1 here and here. The second equation, we have n plus 1 here and there. So this is backward Euler, but in forward Euler, n plus 1 only shows up on one side. This is explicit, cannot be done for stiff problems. This is implicit, and that's the only way we can solve stiff problems. And you can see that with implicit method, which is backward Euler, solution stays very small initially. Well, actually it's going to grow, but not really fast. This one, which is forward Euler, and that is explicit method, the solution blows up and you get 100% wrong answer if you use forward Euler or explicit methods for stiff problems. Okay, so I hope this is useful. Thanks all for watching. For the next video on chapter 6.